everybody, we're gonna do matrices today, which I'm not sure, I don't know if you guys did them last year, but they are pretty fun. They save a lot of time and will really help us in what we're doing today, so I'm excited. So we're gonna learn how to write matrices, identify their dimensions, and perform elementary row operations, and how to use Gaussian elimination, which we learned the other day, but also Gauss-Jordan elimination with matrices to solve equations. So a couple of things that we need to know is what's an entry of a matrix. So I'm just going to show you an example of what a matrix can look like. So it usually looks like this. It's got these brackets, and then it has numbers in it of some sort of rows and columns, like A, B, C, D, E, F, G, H. And these letters can represent whatever's in that spot of the matrix. This is an example of a matrix. There are many, infinitely many matrices. So an entry of a matrix is one of the real numbers that makes up a matrix. So like A is an entry of the matrix, but we can see that there are 11 others. The dimensions of the matrix, we name that by the rows, by the columns. So the dimension is always R by C. So in this case, it goes, rows go down, by the way, because these are rows. So we would call this row 1, row 2, row 3. And these are columns. They go down. So in this case, there is column 1, column 2, column 3, column 4. So we would call this matrix a 3 by 4 because this 3 stands for the rows, 4 stands for the columns. Okay, a square matrix is when the rows equals the number of columns. And a main diagonal, when we're talking about that, is when we go from the upper, I'm going to highlight it in green for you for the main diagonal. It's the upper left, and then it goes diagonally like this, but it has to be usually in a square matrix. So we'd go from the upper left down to the lower right, and we usually call it like this. We would say this is the term in the first row in the first column. This is the term in the first row, second column. This is the row in the first row, third column, and so on. So this would be the term in the second row, first column, second row, second column, second row, third column, and so on. And then these would be the main diagonal. A row matrix is a matrix with only one row, so it would look like this. And a column matrix is going to be a matrix with only one column in it, so it looks like this. Elementary row operations are what we learned before when we're talking about Gaussian elimination. It's the set of operations that can be performed on a matrix and produce an equivalent system of equations. And we'll talk more about that in a minute. And then Gaussian-Jordan elimination is the process of reducing, process of reducing a matrix to reduced row echelon form. We call that RRE for short. Okay, and we'll talk about what reduced, well, actually, I'll just show you right now. Reduced row echelon form will look like this, where you have ones on the diagonal and zeros everywhere else. So if m and n are positive integers, define an m and n matrix. So an m and n matrix would be like a rectangular array. So if you've got a matrix that looks like this would be, the first term would be row 1, column 1. Second, this one would be row 1, column 2, row 1, column 3. And this could go all the way until row 1, the nth term. I don't know how many total columns there are. Row 2, column 1, row 2, column 2, row 2, column 3, row 2, column n. We don't know what the n is. Row 3, column 1, row 3, column 2, row 3, column 3, all the way to row 3, column n. We don't know what it is. Row 4, column 1, row 4, column 2, row 4, column 3, and row 4, column n. So an m and n matrix has m rows and n columns. An augmented matrix is derived from a system of equations that are in standard form with a constant term on the right side of the matrix. So keep in mind when we have a matrix, this is really sloppy, sorry. When we have a matrix, that if, let's just say the matrix looks like this, where we have numbers 1, 2, 0, 1, 2, 3, 4, and 5. This is row 1, column, row 1, row 2, row 3. They go across. This is column 1, this is column 2. So we would say 0 is in the row 1, column 1. We would say 5 is in row 3, column 2. So a coefficient matrix is a matrix derived from the coefficients of a system of linear equations. Okay, so here's what I mean by that. So let's say I had this system of equations here, and we've got 3 equations. To write this as a augmented matrix, this is what this would look like. So here, for part A, I would write this, first of all, as a matrix, and I'm going to take, because I know there's x's, y's, z's, and then finally the constants, I know I'm going to have 4 columns and 3 rows. So I'm going to have 4 columns, 3 rows. And then because this is an augmented matrix, this is our solution, this is our coefficient. So we put this straight line down to kind of separate those two from the coefficients on the left side and the solutions on the right. And now we're going to fill this in. So we see here that there's these coefficients of 2, 1, -1, 1, -3, +2, 0, 3, and 2. So we're going to write those down. 2x, 1y, -1z, coefficient of 5, or constant of 5. 1x, -3y, 2z, constant of 9. 0, pardon me, not a 0, look. This is the x, actually, so it's a coefficient of 3x. There's a 2y, but there's no z on the bottom, so actually there's a 0z with a constant of 1. So there's our augmented matrix, that's part A. So what's the dimensions of this augmented matrix? Well, I know that there are, again, 1, 2, 3 rows and 1, 2, 3, 4 columns. So we say that's 3 by 4 because it's row by columns. Now it says write the coefficient matrix for the system. So the coefficient matrix of the system just is this part right here. So we would say the coefficient matrix is 2, 1, -1, 1, -3, 2, 3, 2, 0. And what are the dimensions of the coefficient matrix? Well, I know there's 1, 2, 3 rows and 1, 2, 3 columns. So we'd call that 3 by 3. So when we're talking about row elementary operations, we talked about this before a little bit. These are operations that